Hello everybody. So now we are going to solve this example here, which is about propane dehydrogenation. So in this case, propane is dehydrogenated, producing propylene and hydrogen, and this process is designed so that we have 95% overall conversion of propane. 95%, this is the overall conversion. It's not the single pass. It's clearly mentioned that's the overall conversion. The reaction products are separated into two streams. So we have the feed going to the reactor, then we have a separator after the reactor, and this is what it means. The products are separated. It means that we have a separator after the reactor. The first stream contains hydrogen, propylene, and 0.555% of the propane that leaves the reactor. And it's taken off as a product. Then the second stream, which contains the balance of unreacted propane and propylene, is recycled to the reactor. The amount of propylene in the second stream is equal to 5% of that in the first stream, and we want to calculate the and this is actually very brilliant requirements. The composition of the product, the ratio mass recycled to moles fresh feed. This is very important, and the single pass conversion, which is also a very important thing. So if you try to draw this flow sheet, this is what you would get. I'll read the flow sheet again, the process description again after reading the flow sheet, after drawing the flow sheet. So we have 95% overall conversion of propane. Okay, the reaction products are separated into two streams. So this is the separator. The products are stream number 3. It's separated into two streams. The first contains propane, propylene, and hydrogen, and we are told that the propane C3H8 in stream number 5 is 0.555% of the propane that leaves the reactor. So this is a relation between the number of moles of propane in stream 3 and number of moles of propane in stream 5. Okay, so this is 0.55% of this propane. The second stream, which contains the balance of unreacted propane and propylene, is recycled to the reactor, which is this stream number 4. The amount of propylene in the second stream, which is the propylene here, C3H6, is 5% of that in the first stream. So this is the first stream, this is the second stream. So there is a relation between the propylene here and the propylene here, and we need to calculate the composition of the product, and this is the requirements that we want to calculate. So let's start with the writing the information that we have, which first is going to be the reaction. We have only one reaction, we have no other reactions, and the additional relation. So the first additional relation is the overall conversion, which is the relation between the number of moles of propane in stream 1 and the number of moles of propane in stream 5. So it's 1 minus 5 over 1, it's 0.95. The second is 0.55, which is the number of moles of propane in stream 5 is 0.555%, which is divided by 100 would be 5.55 times 10 power minus 3 of number of moles of propane in stream 3. Finally, the propylene in the second stream, so it is the second stream. This is the number of moles of propylene here is 5% of the number of moles of the propylene here. So these are the relations that we have. And now let's see what we are going to do next. So the next is performing the degrees of freedom. So for the degrees of freedom table, we have in this mixer we have 1, 2, 3, 4, 5 variables. The number of given variables is 1. I think this originally didn't have this flow rate. This is a basis that I assumed later. Before the basis, it's 1000. It's not given, so we have 5 variables, no given variables. We have 2 equations and no relations, so the degrees of freedom is 3. For the reactor, we have 1, 2, 3, 4, 5. Here I'm doing the calculations using the extent of reaction method. So we have 5 variables plus 1, which is this reaction. For the given variables, there is no given variable. Number of equations is 3, because we have propane, propylene, and hydrogen, and the additional relations is 0, because we don't have any additional relations in the reactor. So we have 3 degrees of freedom for the reactor. For the separator, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 variables, no given variables. The number of equations is 3. We have 3 components, and the additional relations, we have 2 relations here, which are the last 2 additional relations. So this will make the degrees of freedom also 3. Now for the overall loop, we have 1, 2, 3, 4. So we have 4 variables, and there is a reactor inside. So this is going to be included here. So we'll add 1. So it is 4 plus 1. The number of given variables is, in the beginning it's 0 before this number, so it is 0. The number of equations is 3. The number of additional relation is 1, which is the overall conversion. So this makes the degrees of freedom 1. In the beginning we didn't have this number, so the degrees of freedom is 0. I'm sorry, the degrees of freedom is 1. So now we can assume a basis of 1000 moles of propane. I'm sorry. And now the degrees of freedom, or this 1000 is going to be added to the mixer and the overall loop. So these are the degrees of freedom. So the overall is 0. So we can start with the overall, and if we solve the overall, we can add 3 information to the separator, which will make the separator solvable. And after solving the separator, we will calculate the components in stream 3, which will make the reactor solvable, and 2 information that will be given to the mixer, which will make the mixer solvable. So the plan is to start with the overall, separator, and then either the reactor or the mixer. So starting with the overall loop, it's going to be very, very simple. It's a reactive system, because we have a reactor as part of this loop. So we have a reactive system, and for this reactive system we have the as we said in the degrees of freedom table, we have 1 relation and 3 equations. So this is what we are going to use. So I would start with the additional relation, because it's going to give us 1 variable directly, which is the number of moles of propylene in the product. So it is 50 moles. Now given this information, we can start writing the balance equations for propane, propylene, and hydrogen. For propane, it's going to be propane out, which is 50, equals the propane in, which is 1000, plus the extent of reaction multiplied by the coefficient. This is 50, this is 1000. The coefficient is, according to the reaction, it's -1, so xi is 950. Now I know xi, so I can do everything. So I can calculate the number of moles of hydrogen and propylene out. The in is 0, so the propylene out is going to be xi, the hydrogen out is going to be xi, so it's going to be 950 moles for each one of them in the product stream. So this is the first thing. Now we can update the degrees of freedom table. So this is something that you don't need to do. I'm just doing this because I want to show you how the solution is helping for the next steps. So now we have 3 information added to the separator. So the separator degrees of freedom now is 0. And that's it. I didn't do anything else. I didn't calculate anything related to the mixer. So we can solve the separator. So for the separator, I would also start with the additional relations, because they are very straightforward. They are relating stream 5 to stream 3 and stream 5 to stream 4. So we can calculate the number of moles of propane in stream 3, which would be 9009, and we can calculate the number of moles of propylene in stream 4, which is 5% of the propylene in stream 6. So we already calculated them. Now the rest is going to be very simple. We can apply mass balance to the separator. We can apply for any of them. I know that the hydrogen here is going to be equal to the hydrogen here, because there is no nitrogen in 4. The propylene here and propane here can be calculated, or the missing information will be calculated. So hydrogen in equals out for propylene. I know the propylene in stream 4, and I know the propylene in stream 5, so I can calculate the propylene in stream 3. The same for propane, we can calculate the propane in stream number 4. So now we calculated the components in this stream and in this stream. The degrees of freedom of the reactor now is 0, and for the mixer is 0. Okay, and now we can move to the next part, where we for me it's easier to solve the mixer. So the mixer is going to be very straightforward. The number of moles of it can be solved by just looking at the numbers. The propane here is going to be 8959 plus 1000, so it's 9959, and the propylene is the same. So we calculated everything. So after all this, we can look at the results that we have, and based on what we calculated, we can find the requirements in this problem. And these requirements are the the number of moles of or the composition of the product stream, which is dividing each one of them by the total, which is very, very simple. The second, which is an important thing, is the moles of recycled stream compared to the single pass conversion. So in this case, it's going to be the number of moles of propane in stream 2 minus number of moles of propane in stream 3 over the number of moles of propane in stream 2, which is going to be 9.5%. And finally, the moles recycled to moles of fresh feed. So this is the recycled stream 4 over stream number 1, and this is going to be almost 9. And it's not clear here, but it is 9. Okay, so I'll stop here. In the next video, we're going to discuss the results that we have here. They're very, very important results, and they need to be discussst in more details, because this will mean something important for the next let me discuss it here, and then we will discuss the rest in the next video. So for the results that we have here, it's important to note that the overall conversion of the process was 95%. This was a given information that we know from the beginning. So 95% overall conversion, and the single pass conversion is 9.5%. So it's a huge difference. It's from 9.5 in a single pass, it increased to be 95 in the overall conversion. And this is achieved because we have a recycle stream. So this is a very, very good example to show that the recycle is making a very, very, very obvious change in the conversion and the whole process. Compared to the single pass, of course. The second thing, which is an important thing, which is how many moles recycled per moles of the fresh feed. If you and this requirement is actually not required just to calculate any random thing. It means a lot to look at the numbers. So the flow rate of this stream is almost 9,000 moles, while the flow rate of this stream is 1,000 moles. So this is 9 times. So I just want you to imagine that the number of moles entering the reactor, for every 10 moles entering the reactor, 9 of them are recycled from the separator. 9 of them. So the majority of the feed going to the reactor is originally from the recycle stream, not from the feed stream. And this is very, very expected thing. And the reason this is expected, because the conversion in the reactor is very low. And this means that there is a very, very big flow rate of the components that didn't react that are going to be returning back to the reactor. So this makes the load on the recycle stream very, very high. Okay, and that's why we have a very high ratio of recycle to the fresh feed. And this is something that you can try yourself. So, for example, let's say that you have the same problem. And you solve it with different givens. For example, you put the reactor conversion, make it 50%, for example, and then calculate the flow rate of the recycle stream, and keep everything the same. The relations between the separator streams are the same. The only difference is that the given information that you know is the conversion in the reactor, not the overall conversion. So make the reactor conversion, let's say 50-60%, and then calculate how much recycle we have. In this case, you'd see a very, very, very big reduction in the flow rate of the recycle stream. So this is something that is worth trying. So I really recommend that you do it, because this will be very, very clear to show you, or a very good way to show you how the conversion affects the recycle. So I'll stop here, and we will continue in the next video, inshallah. This is the findings just written as points. So I'll see you next video, inshallah. Goodbye.